Hi everyone. So in this lecture we will be looking at the solar photovoltaic systems, which is a part of Unit 2 in Renewable Energy Sources course. So these are the contents. We will be having both parts of photovoltaic power plants as well as fuel cells. But here now we will be discussing about photovoltaic power plants. These are the syllabus contents: solar energy generation of electricity by photovoltaic effect, dependence of a PV cell characteristic on temperature, solar cell output characteristics, equivalent models and parameters for photovoltaic panels, and finally photovoltaic systems and their applications, as well as economic analysis of solar energy. Right. So we all have already discussed in the unit 1 as a part of introduction to this course that solar energy is the most important renewable as well as sustainable energy system because it is replenished and it is freely available. It has grown consistently and become a popular resource of energy. So if we talk about popular, the main reason is that the cost of energy is gradually reducing, so people are very much interested to install these solar PV sources, and these also got several applications, like we can use solar energy for heating purpose as well as for electricity generation purpose. And the photovoltaic panels are placed on the rooftop of houses or commercial buildings in general, because sun will be directly falling on rooftop, right? So they are generally installed on the rooftop, and collectors such as mirrors or parabolic dishes can also be placed and moved for tracking the sun throughout the day, right? So this mechanism is being used for concentrated lighting in buildings. That means this collecting through mirrors as well as parabolic dishes is used even for concentrated lighting purpose in buildings, right? Okay, so typical applications of solar energy are generally electricity supply to residential loads and also far off electrical installations, like how we discussed about the remote places where grid supply is not available. We should take solar energy there for supplying the required loads. And now it also has a major role in distributed generation network, because what is distributed generation? The generating sources, if we place in a distributed manner towards the distributed network, it is mentioned as distributed generation. So solar is a part of distributed generation network as well, right? So how this generation is going to happen? So solar energy can be obtained in two ways: photovoltaics and solar thermal. So that is extraction of solar energy, right? So in solar thermal collectors, the heat energy is converted into electrical energy, whereas in case of solar photovoltaic system, the light energy is converted into electrical energy through photovoltaic effect. Okay. It means we can use the heat energy directly for heating purposes. Otherwise, we can even use the heat energy for electricity generation as well, right? Next, so this solar energy originates from the nuclear fusion reactions occurring in the core of the sun, right? The solar power reaching the outer atmosphere of Earth is approximately 1361 watts per square meter. So per square meter area, we will be having the solar power which is of 1361, that is 1361 watts, and this is often referred as solar constant. So it is an important definition. And the solar power reaching the Earth's surface varies depending on factors like atmospheric conditions, time of the day, and geographical location. And as an average, it is about 1000 watts per square meter. So there is some difference. The solar constant, whatever is reaching the outer atmosphere, is 1361 watts per square meter, whereas the one which is reaching on the Earth's surface, because atmosphere is different. Atmosphere is at a certain height from the surface of the earth, so it reaches atmosphere with an amount of 1361 watts, whereas it reaches the earth surface with the wattage of 1000 per square meter. That is the difference, and it also varies based upon the time of the day, as well as atmospheric conditions, as well as geographical locations and all, right? So if you see, the total worldwide power demand of all human civilizations needs is approximately 17 terawatts, right? That is 1.7 into 10 to the power 13 watts. And the sun provides an enormous amount of energy compared to what we currently need, right? Because per square meter the solar energy is almost 1 kilowatt. So 1000 watts is nothing but 1 kilowatt. So it is just per square meter only. You understand that there is lot of area on this earth, so the sun is providing enormous amount of energy when you compare with what we currently need. So it is estimated that the earth receives about 10,000 times more energy from the sun than we currently use, right? There is huge potential of solar energy, so this is called potential, right? Okay, and utilizing just 5% of solar energy reaching Earth's surface would indeed be significantly more than what the world currently requires. And the energy radiated by the sun on a bright sunny day can be indeed approximated to around 1000 watt per square meter at the Earth's surface under optimal condition. So this 1000 watts is on a bright sunny day under optimal condition. Okay, and the irradiance is the one which is having units of kilowatt per meter square, and irradiation is the one having kilowatt hour per meter square. That means irradiance is with respect to power per square area, square meter, and irradiation is energy per square meter. Okay, generally the irradiation is the one which is used in this course of solar energy. Okay, right, let us see what is this solar radiation spectrum, right? With this solar radiation spectrum we will close this lecture first. So if you see here, there is sunlight at top of the atmosphere which is more than that is falling onto the surface, right? Just now I told. And there is 5250 degree centigrade black body spectrum is there. This black color one is that, and yellow color is the one which is there on the top of the atmosphere. And radiation at sea level is nothing but on the surface, so surface is referred with sea level. And if you see, it is in red color, and there is difference between yellow color and red color, because the one which is coming onto the atmosphere and reaching the sea level is different, right? That's why. And you can observe there is some dips in between for different wavelengths, at different wavelengths. That means if you observe here there is a dip with O2 indicated. That means it is the absorption band of oxygen present in the atmosphere. So since the radiation is completely absorbed by the oxygen, the one which is reaching the sea level is less. That's why there is a dip, right? That's how you need to understand. Similarly here there is a more dip because of ozone, because this wavelength gives the ozone for absorbing it, for absorbing solar energy or radiation, right? Similarly we have H2O absorption band, and different H2O bands are there, and CO2 band is also there, right? So you can, this is the understanding about solar radiation spectrum. And there is UV wavelength range, visible wavelength range, as well as infrared wavelength range. Okay, so okay, this is about solar radiation spectrum. We will continue in the next class, right? Thank you.